So we've talked before about how ions can dissolve in water. And just as a brief review, basically we have a chlorine ion that's negative, and the water molecules will orient in such a way that the hydrogens, which are partially positive, are close to the chlorine. And this process is called hydration, right? But it can also be called dissociation, right? Because the ions are breaking apart. Now, ion concentrations are really important because they can influence a lot of biological processes. For example, if you're a runner, you know you should drink electrolytes, or if you're an athlete, you know you should drink electrolytes because you don't want your ion concentrations to get too low. It can cause heart problems. And so when we talk about this, we are going to define strong electrolytes, weak electrolytes, and non-electrolytes. And then we're going to talk about equivalence. Now, how a solute behaves when dissolved in water really depends on if it's ionic or molecular in nature. Ionic solvents or solutes will tend to form ions, which are just charged particles, when they're dissolved in aqueous solutions. When a strong electrolyte is dissolved in a solution, it's going to dissociate completely into its ions. So a strong electrolyte dissociates completely into ions, right? And for us right now, right, ionic complexes are going to be strong electrolytes, okay? Other things, which we'll talk about in the next chapter, are acids, strong acids, and strong bases are also strong electrolytes. Now, when we put these, and when we show this dissociation, you just show the ions that are breaking apart. It's almost the opposite of a net ionic equation, right? And so we show the ions that are breaking apart here. You may have heard about electrolytes because of Gatorade. Basically, that's just solutions of ions and some sugar, so it doesn't taste terrible. And then also another thing to recognize is that ionic solutions are going to conduct electricity. And so they're going to light up light bulbs very, very brightly. Now, you can also have weak electrolytes. These only partially dissociate into ions. And these are things like your weak acids and weak bases, which we're going to talk about in the next chapter. Vinegar is a really good example where it is a weak acid. And so what that means is that with vinegar, it mostly stays in this form and only a little bit break apart. And so that means only a little electricity is conducted, and so the light bulb is not as bright. Okay, and you can see the molecular view here. Then we also have non-electrolytes, and these are substances where no ions form. And these are your covalent molecules or your molecular molecules. Remember, we're using those as synonyms. These will be things like sugar, ethanol, ethylene glycol, and they stay together and they do not conduct electricity. Now, as I mentioned before, the behavior of many biological systems is dependent on the concentration of electrolytes. And so to keep up with this, we use something called equivalence. And this is another concentration measurement, and this is just the number of moles of an ion corresponding to an electrical charge, right? And when we talk about equivalence, a lot of times it's shown as equivalent per liter, right? Which equals the equivalent per mole of the ion times the molarity, which is moles per liter. And so the moles cancel and you're left with equivalents per liter. Now, the equivalent per mole of ion equals the number of charges on the ion, right? So for example, sodium has a charge of +1, so the equivalent per mole is going to be 1, okay? Magnesium has a charge of +2, so the equivalent per mole equals 2. If you have a negative ion, like carbonate here, its equivalent per mole is also 2. We just don't pay attention to the negatives here. Here are some electrolyte concentrations that you would find in blood plasma, and they are represented in milliequivalents per mole, and that's just that milliliter prefix or the milli prefix from the metric conversions. So here are other ions that we see in intravenous replacement solutions, and they're different milliequivalent concentrations. Two of the most important cations in the body are sodium and potassium, and you will notice that sodium and potassium are in all of these. Proper cell function and the regulation of muscles and the nervous system depend on that sodium ion to potassium ion ratio in the cells. And particularly if your potassium ions get too low, you will have trouble with your heart not beating properly. So my father used to go play golf, and he would become dehydrated on the course and would have chest pains. And so what we figured out is he needed to drink a Gatorade as he was playing, and a few less adult beverages, and then that went away. So it's something that you run into pretty commonly, and so it's good to be aware of that. So you need to really watch out with cases of dehydration and things like that. So let's come here. So for a solution that is 5 times 10 to the negative 3 molar in phosphate ions, calculate the concentration of phosphate ions in equivalents per liter and milliequivalent per liter. So if we are looking for something in equivalents per liter, right, we're going to take the equivalents per mole ion, which is related to the charge, and multiply it by the molarity, which is the moles per liter, and we're going to see the moles cancel and we'll have equivalents per liter. So when we look at a phosphate ion, right, it's important to remember that a phosphate ion is PO4 3-. So that means it's going to have 3 equivalents because its charge is 3-. And then we're going to multiply it by the molarity, which is 5 times 10 to the negative 3 moles per liter. When we do that, our moles of phosphate cancel. We're left with equivalents per liter. We do this math and we get 1.5 times 10 to the negative 2 equivalents per liter. Now, we also are asked to get this in milliequivalents per liter. So we take 1.5 times 10 to the negative 2 equivalents per liter. And we know from that first chapter that in 1 liter, there's, I got it backwards. Okay, so let's talk about how I figured out I got it backwards. I don't want the liters to cancel because I want my units here to be milli equivalent per liter. And as I was doing this, I said, oh, wait, something's wrong because these liters would cancel. I've made a mistake. So I've caught that by looking at my units and understanding they're going to cancel. And I was trying to cancel out the wrong thing. So we know there's 1,000 milli equivalents per equivalent, right? And so now our equivalents cancel. We're left with liters, which is what we're looking for. And we're going to multiply by 1,000. And that would give us 15 milli equivalents per liter. So watching for those units to cancel is always really helpful. As always, if you have any questions, please feel free to stop by my office. And for us, this completes Chapter 6.